Thank you for taking the time to be here on a lovely Thursday evening. I'm Neha. I'm a software engineer at Yugabyte, and today I'm just going to be walking over what it takes to build a change data capture and async data replication in a distributed SQL database like Yugabyte. So I think before going into the details of change data capture, I want to just set some context around what is Yugabyte DB and what is a distributed SQL database. So if you look at databases today, you can broadly divide them into two categories. On one side, you have the SQL SQL databases, which are relational, they handle transactions very well, strongly consistent. They have a very flexible query language. You can do joins, aggregations, grouping, right? So very flexible query language, but they're typically single node databases. They don't scale out very well. On the other side, you have the NoSQL type of databases, which are very good at scaling your data. They have replication built in, they're highly available, but they're not very flexible in terms of the type of queries that you can run on such databases, and they're also not strongly consistent. Most of these databases are eventually consistent, so your applications need to handle the fact that the data that you're reading may not be consistent, right? So what happens as a result of this? If you look at any application tier today, most of the enterprise applications will have a mix of a variety of these databases. So you'll typically have your SQL databases that are used for source of truth type of data. You'll have your NoSQL databases that are used for scale out data like maybe tracking events or order events, etc. And then you might have maybe some in-memory databases like Redis that are also used on top of that. And then this entire setup is replicated in all the data centers that you're running in. Now you're shifting the complexity from the database level to the application level, because now applications need to keep track of making sure that all the data across these various data sources and data centers are in sync. So that's where distributed SQL databases like Yugabyte come in. Why does your data tier have to be so complicated? Why can't we do better engineering and get us where we need to be? So we're trying to bridge the gap between the SQL and the NoSQL world, and coming up with a database that has a flexible query language, is strongly consistent, and can also scale out really well and is also highly available. So with that overview, I want to go into a little bit of details about what a Yugabyte cluster looks like. So typically your Yugabyte cluster will have multiple nodes, at least 3 nodes. And your data is divided into shards, what we call as tablets. So every table will be split into a number of tablets, and each tablet is 3-way replicated with 1 tablet on each node. So that way you're able to handle node failures, and still your application reads and writes are unaffected and can continue. This is what each node of Yugabyte looks like. The top half is a stateless query layer, which takes in client requests, does the query planning, figures out which data needs to be read, where that data resides. And then at the bottom half is what we call as the DocDB layer, which is a scalable storage layer. And that's the layer that's responsible for sharding your data, storing the data on disk, and taking care of raft consensus to make sure that data is replicated to majority of the nodes. The data that you're writing is replicated to majority of the nodes. And because your query layer is stateless, your client apps are agnostic of all the sharding replication that's happening. They can, talk to any node in Yugabyte cluster and get whatever data you have written or read, right? Now, if you look at any application that you're building, it's a very complex ecosystem, right? You're not going to be using databases in silo. You'll typically have a database. You'll have some application that's looking at your data in the database and doing some things on top of it. For example, you might have a search index that's indexing some data. You might have some notification service that needs to be invoked whenever, let's say, a new user gets added to the system, right? So that's where change data capture comes into play. So you have your database cluster, you have some data that's going into it, and based on that, you want to generate events that are now being consumed by other applications. So you might have, let's say, a new user gets added to a table. You might want to have a notification service handle that. You might want to index that data. You might want to update some analytics or statistics that you have for users, right? You might also want to use that to update another copy of the database that you have in a remote data center. Now, change data capture is, it's a pretty widely known concept. It's done today for most databases. So what does it really involve, right? How does it work today in relational databases? So all relational databases have what is known as a write-ahead log. So whenever any data is written into the database, it first gets written into a write-ahead log. And a typically write-ahead log will consist of rows like this, something like at time 100, row 20 got written, row with ID 20 got written, and I set the column 1's value to 200. At time 103, row 18 got written, and I wrote the value of column 2 to foo. Right, so you have a sequence of writes that have happened in your database, and change data capture is now basically simply reading those writes and streaming them out to whatever application is interested in it. Okay, so that sounds fairly straightforward, right? What's the complexity here? Well, the distributed aspect of the database adds the complexity. Now what happens is, like I mentioned before, one table's data is divided into different shards, and these shards are stored on different nodes, right? Which means that your write-ahead logs are also stored across different nodes. What that also means is if you have a transaction that's writing multiple rows, the writes for those rows are now written on different wall logs on different nodes, right? So we need a way to consolidate that information and correctly stream that data out. So that adds a layer of complexity. Because it's a distributed database, and by nature you typically use distributed databases when you have a large amount of data. Now even being able to scale to a large number of consumers becomes important. So we need to be able to design this right such that we can even handle a large number of consumers. So this is a very high level overview of how our CDC is architected. So every Yugabyte node, what we call as a T server, so that those are the nodes that are keeping track of user data, has a component called as a CDC Producer. Now this CDC Producer is responsible for tailing all the wall logs that are on that node. Okay, and then you might have some CDC consumers who are going to be reading data from all of these CDC producers. So every application will now require reading or streaming data from multiple CDC producers and using that data for your needs, right? So you might have a consumer A, which is, let's say, consuming the events for a notification service. You might have another consumer which is consuming the events, let's say, to update some search index. They're all now streaming data from the CDC producer.
So what does CDC mean?
Change data capture. So it's an acronym for that.
I assume there can be filtering on all this. Does this happen at the consumer level or down in the...
So today it happens at the consumer level. We don't support we support filtering at the table level. So I can say that, hey, give me change capture only for 3 out of the 10 tables that I have in my cluster. But you can't filter more granularly. That needs to be done on the consumer today. But we want to add that in. So we want to be able to support something like, hey, I want to capture a stream of data, but only for maybe, column country where country is equal to US, right? Yeah. So that's still not there yet. Right now, the granularity is at a table level.
But at the consumer level, it is there. You can filter it there.
At the consumer level right now, no, you can add it in. So we have like a consumer library that you can use, or we have a sample consumer written that you can kind of use for your purposes. So you can modify that and change it to do whatever filtering you need. But yeah, the onus is on the application developer who's actually using CDC right now.
And this is not the notification that's built into Postgres. This is some other notification.
That's right. Yes. This is not the Postgres notification. Right.
So for example, if I have a transaction which, say I have 3 tables A, B, C in each of the T servers, and the transaction I'm trying to write on all those 3 tables at one shot,
right?
And the consumer gets the data whole.
Yeah. So I'm going to come to that.
Okay.
Yeah.
See, like, how will you cover the latency? Like, collating everything to one consumer.
We are not collating, so I'll come to that in a bit. So right now, this is just a way of showing that you have one consumer application, but you can actually have multiple instances of that, each kind of consuming data from, let's say, a set of T servers, right, or one T server. Yeah, I think there was a question back there.
You said you'll come to it.
Okay, all right, perfect. Okay, so kind of before we go into how the producer works, I want to just go over how writes and transactions work in general in Yugabyte, right? So Yugabyte is three-way replicator, like I mentioned before. We use RAF consensus to make sure that we replicate it in a consistent manner. So the way it works is we have, out of the three replicas, we designate one replica to be the leader, what we call as the tablet leader. All the writes go to the tablet leader. And then the tablet leader is responsible for replicating those writes to the other two replicas. And then the tablet leader waits for majority of the replicas to acknowledge the fact that he have written the data, and then it responds back to the client, right? So at every point in time, at least two nodes out of the three would have the write.
By the way, what does REF stand for?
So RAFT is a consensus protocol that's...
What's an acronym for?
I don't think it's an acronym for anything. It's just the name, yeah.
And also, say, if I'm running my application, say 5 different data centers, so this RAF protocol will happen within the DC and across DC, or this diagram?
So it depends on how you set up your Yugabyte cluster. So if you have one Yugabyte cluster that is across all your DCs, across all your regions, then yes, it will happen across regions. So which means that your every write will incur the cross DC latency.
Oh, synchronously. Right?
Correct. Because at least two have to, let's say you have 3 data centers, right, 3 regions, and you have one replica in each region. Then for your write to go through, at least 2 of the regions need to have act the right.
So I think my question was, like, say I have a 3-node cluster in each of the regions. Like
Okay.
region A with
So you have separate clusters.
exactly
Okay.
3 in each DC.
Yes.
And if one DC goes down, I want to do a failover to the other one.
Right.
So in this case, if I'm issuing a write to one of the data centers,
Right.
will the replication happen asynchronously or?
Asynchronously, yes. Yes. So that's exactly what I'm going to go over in the presentation. Like, how do we handle this mode where your application is happening from one data center asynchronously to another data center? So, yeah, so this is how your raft happens. This is how the writes happen in Yugabyte. Now, what happens in case of transactions? Now, transactions work a little bit differently, where we have this concept of a transaction manager. So let's say you have a transaction that's writing a set of rows. For simple reasons, let's say you're writing a row 1 equal to value 1 and key 2 equal to value 2. That transaction first goes to a transaction manager. Now, all of the Yugabyte nodes can act as transaction managers. So it will go, whatever node the write hits, that ends up acting as a transaction manager. The transaction manager creates a status record. Status record is just some metadata that we keep on our end to kind of keep track of, whether the transaction has started, has it committed, or has it aborted. Once this transaction status record is written, the transaction manager then writes what we call as provisional records to the tablet leaders. So in this case, you have written 2 rows. You've written K1 equal to V1 and you've written K2 equal to V2. The tablet leader for K1 might be one node. The tablet leader for K2 might be another node. Now both of these nodes receive a provisional, do a provisional write. Now what is a provisional write? Provisional write is something that we've written in our walls. So we know that this write happened, but we've not yet made that write visible to any reader because the transaction has not yet committed. Now, once the provisional record is written, you actually commit, the transaction manager will commit the transaction. And once that's done, we trigger an apply of the records, which means that you basically make the records visible to any reader. Now, as you see in this diagram, what's happening here is you have provisional records that are being written to wall at one point, and then at a later point, you have a commit that's going in, right? So as a result of that, your wall data ends up not being ordered, right? So here's just some example. You have at time 10, you have some write that happened that was not part of a transaction. At time 11, you had a write for transaction 1. At time 12, you had a write for transaction 2. Now, note that both of these are provisional records, so they should not be made visible to anybody. So they should not be made visible even to CDC consumers. And then you have at time 21, you have a commit that happened on transaction 2. Now the interesting thing here is note that transaction 2 committed before transaction 1. But the provisional record for transaction 2 has happened after one provisional record for transaction 1, right? So we need to, on the CDC producer side, CDC producer needs to make sure that we are doing some ordering of the wall records before sending them out to the consumer. So that's one. So now what will happen is CDC producer will kind of run through this, order it, and then generate a set of ordered events that it will send out to CDC consumer.
And you knew about them because it sent provisional records?
Correct. And those records are recorded in the wall. Right, so this kind of distributed nature of having these commit records and provisional records adds a level of complexity that needs to be handled. So, kind of two optimizations that we've done on the CDC producer side. One is the reordering of wall records that needs to be done for transactions. The other is if you look at the we have a CDC producer that's running on every node. Right now, we made the decision of tying a CDC producer to a tablet leader. So let's say that there's a node, which has a replica of a tablet, but that node is not the leader of that tablet. Then the CDC producer on that node won't emit changes for that tablet. Only the tablet leader's CDC producer will emit changes. And there were two reasons why we went with that decision. The first and the more important reason is that we have certain optimizations that we've done, to make writes pretty fast. One of those optimizations is this having a log cache, which is there on every tablet leader, and it maintains. It's like a write-through cache that it maintains for the wall. Tying the CDC producer to the tablet leader meant that we could read from the cache. So instead of accessing the disk and reading data from the disk, wall data from the disk, we could just for the most part read data from cache, which is much faster. And the other thing that it helped us with is since the tablet leader knows very accurately what the last write was on this tablet, we are able to emit more accurate metrics. So your replication delay, etc., is more reliable because the tablet leader knows exactly what it is. If you do it from a follower, there may be a replication lag, in which case the metrics won't be so accurate anymore. Okay, now I'm going to drill deeper into how we leverage the CDC framework to do async data center replication. So just tying this back to one of the questions that you had about data center replication, right? In Yugabyte, synchronous replication is the default. What that means is I can have one Yugabyte cluster that's spanning across multiple availability zones, right? That's one option. I could have a cluster that's spanning across multiple regions. I could also have a cluster that's spanning across multiple clouds. Now in all of this, each node might be in one availability zone or one region or one cloud, and by default, when you do a write, you have to wait for at least two of the regions or clouds to act the write before you return, right? So synchronously, we replicate by default. Now, sometimes synchronous replication may not suit your application well. I think one of the top reasons for that is your application is very sensitive to cross-region latencies. Like if you look at example number 2, if your regions are US East and US West, typically you will have a 50 millisecond roughly region latency, right? And your application doesn't want to handle that. So that's when async replication comes in. So, yeah.
It's like the available.
Yeah.
So availability zone is like within a given region you
Correct.
split them into multiple zones.
Yes. So AWS has this availability zone concept, right? So it's that.
Within a region.
Yes.
Will come when it is multi-regional or a multi like a hybrid cloud.
It depends on your.
Availability zone, it's already the latency will be low.
Correct. So so you can do synchronous even across regions. So you can deploy a Yugabyte cluster. These are today available options. But if your application is sensitive and you don't want to handle the 50 millisecond latency that you might get across regions, then you can choose to go with async replication.
But what I have to lose with the consistency?
Yes. So that's the other thing that comes into play, right? So your application cannot handle cross-region latencies, but obviously now the downside is if you do simultaneous writes to the same row, now who wins, right? Like which write wins. That's where the second requirement, your application is able to handle conflicts comes into play. So, your application can be structured in such a way that maybe user A's writes will only go to one data center, user B's writes will only go to the second data center, so you won't have conflicts, in which case you can go ahead and use async replication.
So what will happen like if a two request goes to two different DCs and changes the same row?
Yeah, so
the database record, you will capture different values and because application does a read on one side, you get different value, and if it goes to the other side, it gets different value.
No, so it will eventually be consistent. So what that means is, let's say I write on one data center key 1 equal to A, and I write on the other data center key 1 equal to B. Now they both replicate, right? Now depending on what timestamp each of the records has, so if A's record is at time 100 and B's record is at time 105, B wins. So the last writer wins, right? So eventually on both sides, K1 equal to B will be persisted.
But if the replication hasn't caught up, then if I'm reading data from both sides, I might see conflicting values.
Correct. If you read from both sides, yes. So which is why, like, I think for most applications, synchronous replication, if you can handle the delay, that's the easiest for your application to deal with. But if you're very sensitive and you're okay with your app taking that overhead, then we wanted to be able to provide that flexibility. Now, in a very simple scenario, this is what a 2DC architecture looks like. You have two different Yugabyte clusters. Each cluster has its own T server. Each T server has its own CDC producer. On the other side, you have another Yugabyte cluster, and each cluster now has its own CDC consumer. So this kind of demonstrates one-way replication. If you want two-way replication, it's pretty much the same, where now each T server has a producer component also and a consumer component also. And again, for simplicity, I've drawn number of nodes to be the same, but that's not a requirement for us. So you could have heterogeneous clusters, like one cluster could have 3 nodes, the other cluster could have 5 nodes. We are able to handle that. So let's drill more into the details of how a CDC consumer works, right? Now, what happens is CDC Consumer is the component that's continuously polling the CDC producer for data. So it's basically saying, hey, get me all the latest changes that happened since some checkpoint. Now, the CDC Consumer gets some data from CDC producer. Let's say that it gets 2 rows, K1 equal to B1 and K2 equal to B2. Now the CDC Consumer will need to write the record for K1 and K2 on its own cluster, right? So it has to send that write to the tablet leader for K1, and it has to send that write to the tablet leader of K2. Okay, now there's an obvious question here, right? We've introduced one hop here, right? So you have data coming to CDC Consumer, and then this CDC Consumer is sending this data out to somebody else within that cluster, right? So what can we do to make this better and improve performance? So a solution to that was using tablet mapping. So what we try to do is, when you are setting up replication between 2 clusters, we try to intelligently map the consumers and producers such that whatever set of rows that you're writing on one side, like the keys that you're writing on both the sides, that key space matches. So let's say that you have, your data set is such that one shard has key 1 to key 100 on the producer. We'll try to make sure that the tablet that we choose on the consumer side has the same key space, key 1 to key 100, right? So that way you are kind of mapping the two together, so you don't have to send that write out to another leader. So what happens as a result of that is, your consumer gets the data from the producer, K1 equal to B1 and K2 equal to B2. But now that K1 and K2 are local writes. So you're just writing them on your disk, right? You're not sending it somewhere else. Now, the other interesting thing that happens is, now imagine cross data center will always have some replication delay. So let's assume that, a single one round trip delay is 40 milliseconds. Now consider what happens as you are doing writes. Let's say that I do 10 writes on the producer. The consumer polls for it. I get those 10 writes back with a 40 millisecond delay. So after 40 milliseconds, I get 10 writes. Then I do the 10 writes. Then I call the next set of 10 writes, and the producer gives me 10 more writes. I again write those 10 writes, but now this time I've gotten another 40 millisecond delay, right? So over time, that network delay will start accumulating, right? So if you write on the consumer at the same rate at which you're writing on the producer, you will always result in some replication lag, which will keep increasing, right? So to handle that, what we do is we aggressively batch on the consumer. So the premise is simple: writing one batch of 100 records, for example, is going to be much faster than writing 100 batches of one record each, right? So with that in mind, we try to batch very aggressively on the consumer. So we'll get whatever data the producer has and try to write it in one batch on the T server. So it goes as one raft write. And
How do you size the batch?
sorry?
How do you size the batch?
We have a max cap, but that cap is pretty big at about, right now I think it's 8 MB that we use as a cap. So we've had a couple of folks trying us out, POC, trying out 2DC in POC settings, and we've seen replication delay consistently under 500 milliseconds even when it's been running for days. So some of these optimizations have really helped us a lot.
And is it the same model for transactions? I know you're talking about transactions earlier. So
Right.
transaction replication.
Right. Yeah. Yeah. Now, the next thing is producer cluster changes, right? So, given that it's a distributed system, we need to be able to handle node failures, right? So, assume that you have some CDC consumer that's replicating, consuming data from some CDC cluster, which has, let's say, 3 nodes, right? Now, what happens if one of those nodes dies and a new node is brought up? Your CDC consumer needs to understand that this node has died and needs to understand which new node to connect to in an automated manner. Like, it shouldn't need manual intervention, even though they are 2 separate clusters, right? So that's where we used a smart YB client. So it's basically Yugabyte's cluster-aware client, which is keeping track of all the topology changes that are happening even on the producer cluster, and using that to map the consumer tablets correctly. So this kind of makes the 2 clusters operate in a pretty automated fashion. So even when node failures happen or things change on the producer side, the consumer remains unaffected and is able to handle those changes automatically.
So if I'm
Yeah.
doing, if I have a 2DC cluster,
Right.
that's set up for a asynchronous replication, then the RAF consensus will kick in only for that local within the region, and across region replication will happen through the CDC.
Correct. Yes.
Okay. And is it pull based or push based?
Pull based. So the consumers are continuously polling.
Say if I set up say 5 consumers, so how do you make sure that they don't step on each other?
Yeah, so we have some throttling that is built in as well. So each consumer, so let's say even when you have one consumer with a large number of tablets, we kind of throttle the way we poll for changes. On the producer side too, if you have a lot of requests that are incoming, we'll send out like some specific error message. And when the consumer gets that error message, we back off. So we have some exponential back off that is built on the consumer side to kind of reduce the rate at which you're polling.
So my question was mainly if I have say many consumers
Yes.
and polling at the same time,
Yeah.
how do you make sure the consumers don't see the same record, don't poll the same record from the producer?
Oh, you want the consumers to handle.
Like
What?
end producers and end consumers, and when consumers are polling continuously,
Right.
you have to make sure that whatever consumer A polls, consumer B doesn't poll the same set of records. Right?
So that is a slightly different thing, right? So this is now I'm assuming here by this you mean that all your 5 consumers are operating for the same app, right? Because you don't want one to see the other. So in that case, now your app needs to handle how you'll split the consumers. So your app needs to take care of not having 2 consumers consume data from the same tablet.
In this case, where you're talking about, think of the 2 data center feature itself as an app, which is using the change CDC mechanism, right? In that case, we have arranged it such that these consumers are 1 per T server, am I correct?
Yeah.
Oh, okay.
If you have a 10 node cluster, then there are 10 consumers, and they know what their responsibilities are. So this particular app, which is the 2DC app, which is a client of this CDC mechanism, is doing that intelligence. It's sort of built into the 2DC feature.
So basically, two consumers will not pull from the same.
They won't.
Correct. So that's why the tablet mapping that I was talking about, right? That's the part that handles like which consumer will be polling for which from which producer. Okay. And then the other thing is also replication is based off wall logs, right? So we are tailing wall logs and sending data over. Now what happens if your producer cluster what happens if your consumer cluster goes down for an extended period of time? Will the producer end up purging the log records because you only retain it for some X amount of time, right? So the question is, how long do we retain those logs? So what we've done here is tried to make our system more intelligent. So we have metadata which we keep updating based on how far your application, what your application lag looks like for across all the different consumers that you have. And then based on that, we automatically decide, what is like the log that I need to retain. Like, hey, I can purge everything from operation ID 100 and below, and everything 100 and above I need to keep. So there's metadata that we keep to maintain that information and use it to intelligently figure out which logs to purge and which to keep.
If you have a slow application,
Yes.
it gets its burst and then it thinks for a long
Right,
time.
right.
The metadata won't throw away.
No, it won't throw it away. So as long as you have disk space, enough disk space to retain the logs, it will keep it. If you start running out of disk space, then to maintain a healthy cluster, we'll purge the logs. In which case, now what your consumer will need to do is sort of use a backup restore type of mechanism where you already have some data, you kind of restore that raw data and then start streaming again.
That's all invisible to the application.
Yes. So the backup restore right now, you need some manual intervention where the admin needs to go in and explicitly trigger. Like you'll be able to see that, hey, your consumer has fallen off, but you need to trigger then the backup restore to get it started. But yes, making that more automated is also on the roadmap. Although realistically, most people, what they end up doing is they'll end up retaining logs for like maybe 24 hours or more, right? They typically have a lot of disk space to retain that. So we haven't seen people really needing that mechanism or clusters being down for that long.
Okay, so somebody's doing analytics and they gather in a whole bunch of records and then
No, not as much.
do their slicing and dicing and whatever on them, but they got if they're within 24 hours, they're probably good.
Yeah. So for the most part, if you're able to retain that much of logs, you're going to be good. Okay. So this is just like an overview of all the different 2DC optimizations that we had to do, consumer optimizations. So one was kind of mapping the tablets. So you eliminate that one hop. The other one was batching aggressively. The third one was using an intelligent client, so any producer changes don't impact the consumer. And then finally, it was kind of doing a more intelligent log retention.
Is the batching size autonomously configured, or is that something that's, you decide at the deployment time that I want a batch size of 2 megabytes away?
Yeah, so today we default to using up to 8 megabytes, but it's a configurable option, so you can tune it if you want to. Yes?
How much does this apply to non-Yugabyte consumers? I'm assuming you could send changes to like Kafka or
Yes, yes.
like that. How much of that is implemented and how much of it is like really specific to this
To data center, right?
If we wanted to do a new integration, would that be like re-implement all of this, or how much of this work is available to not?
Yeah. So right now the producer side optimizations are available for everybody. Like it's for pure 2DC also and pure CDC also and data center application also. The consumer optimizations today are only for 2DC. We are planning though to change that and kind of make it more available. CDC right now is still in beta. 2DC is GA for us, or rather will be GA next week. CDC is something that we want to make generally available soon. So we are looking at least having a more production ready version of it in June when we release 2.2. So that's when some of these optimizations will come into a very generic client.
And at that point, you'll be able to do things like Kafka and other things.
Yes. Today also we support emitting events to Kafka, but none of these optimizations are there in the consumer.
What does the application interface to this look like? What,
So when you're using data center application,
you have an application, you want to get notified, you want to be notified. What do you have to do? In particular, say you're using JDBC for Java. Does this come through the JDBC interface, or is it you go around through the back door somehow? Or
so this is so just trying to understand the question better. So this is specifically if you have a generic CDC consumer. Okay, so right now we support the one consumer that we support is a Kafka consumer, which means that you can start up this consumer, it will read the changes that are happening in Yugabyte and it will emit events to some Kafka cluster and topic. Yeah, and we have like some code that we've put out on how to write a consumer, so people can use that to write their own consumers if need be, but for now it's only Kafka.
And it's a custom RPC, it's a custom proto-based thing. It's not JDBC, right?
It's not JDBC, it's a proto-based pull. So we use protobufs, like Google's protobufs, and we use RPCs based on that.
so you need about 3 or 4 layers to get implemented here.
Yes.
If you're running a Java shop,
Yes.
then you got to go play Kafka. You know, if you just need databases, this is a lot of stuff you got to learn.
Right.
That's
Yes.
not good.
Yes.
The SDK around CDC is something that will come in 2.2 right now.
Correct.
CDC is more of an internal feature that we are using for 2 data center, but really productizing that so that an end user can talk to it from Go or Java, what that SDK looks like, and freezing the API, because once we go production, we can't change that.
Freezing is strong, but I mean, just having an API that you can get at from your programming language of choice. Yeah, these things change. It's all.
So that's more in the 2.2 time frame. So it's about 4 months away at least.
Yeah.
But it's like you said 2DC replication, but it can be NDC replication as well.
Yes. Yes. Yeah. And end-to-end. So how many ever producers, how many ever consumers.
And that's available as of now?
Yes. So 2DC is fully available right now. CDC is the one that's in beta. Right now it only supports a Kafka client, but we want to make that more generic. So like you said, right, any client application should be able to use this feature. So that's the intention, what we want to get to by June.
So DJ, what additional feature do you want to have with the CDC?
So CDC, well, in terms of features, it's right now, it's you want to be able to use it for, right now it only emits to Kafka cluster, right? But if you're not using Kafka and you want your, some generic application, let's say you want to take the chain stream and update some indexes in Elasticsearch or whatever your application may be, you should be able to stream that data out of Yugabyte, right? So that's what that piece of how to write that client, that's the part that we're going to be supporting 2.2.
Another question is that you don't plan to support like more general like transaction ordering of the changes. Right now it's basically like a tablet order, right?
Yes.
So you plan to support like
Yeah, we do, but that's not, I think that's not going to be near term. That will be, closer to maybe some release that we have towards the end of the year. So first, what's going to come in place is the CDC generic client. So it's like kind of available for everybody to use, and then being able to have the CDC consumer itself handle transactions. That's going to be, it's going to come in as a next step.
Well, those consumers, are they planned to, like there's failover for the applications, which is all visible to Java, for instance.
Right.
Will they fail over in the same way? If a node goes missing, then...
Yeah. So the idea will be to have like, some component that's Yugabyte cluster aware, similar to what we've done with the 2DC consumer.
I assume Kafka's a ring or something like that. You put things on it and it goes and finds the guy, but...
In the Kafka cluster or in the Yugabyte cluster?
I don't use Kafka. So.
Okay, yeah. So Kafka is also a cluster of machines, and you kind of just save what topic you want to emit your events to. On the Yugabyte side also, it will sort of be similar, where your CDC Consumer, like the vision is that your CDC Consumer should just be able to connect to the Yugabyte cluster without caring much about, what nodes are part of the cluster, or, if one node fails over to some other node, it shouldn't need to bother about all of that. It should just be able to connect to the cluster and stream data out. Yes.
One idea has been whether we can expose the change data capture log as a bit where a Yugabyte table itself, in which case something like using the vanilla JDBC interface will just work. So it's kind of like a non-materialized table, it's a virtual table, but you can use your vanilla API to interact. So that was one idea, we haven't fully spec'd that out. The other thing is there's a request for not just the post image of the change, but people want to know the pre and post, like, I want to know not only the new value of the row, but can you give me the old value of the row that's changing? So, yeah, so that's why the CDC as a generalized mechanism is a bunch of work for us, but we will be doing it.
Yes, you are.
That was the thrust of my question is, so it looks like there's a mapping between tables and rows up in the SQL layer, and then you've got a key value store down at the storage level, like all your CDC examples were key value.
So they were key value, but it's mostly like you're writing a row. I just use key values for simplicity, but it's not actually key value. You're like writing a row. Yeah.
Okay.
Like a row identifier equal to data for that row.
Okay, so then I guess the other question is, what isolation levels does Google support, and how does that play into all of this?
Yeah, so we support two isolation levels, snapshot isolation level and serializable level. How does this play into, so for the most part 2DC and CDC sort of remains unaffected because what you are sending out is committed records. The isolation comes into play when your transaction is in progress. So the way it works, like what sort of locks will it hold while doing the transaction, is what isolation sort of dictates. CDC only deals with things that have happened after the transaction is committed. So it's sort of independent of it.
But because of the async nature of the two cluster thing, there's going to be, across these two clusters, it's going to be eventually consistent. So we won't be able to give you the same serializable isolation level, or even suppose you have a unique index constraint on this table, you will be able to violate. So the 2DC feature has to be used a little bit more carefully.
Yeah, that's what I was going to ask, because if you've got a distributed transaction, you will maintain locks during the transaction and so on. And now, okay, we're going to commit. So we do the RAF protocol, and everybody says they're committed, but all that is going to happen kind of asynchronously. And now the consumers are getting, oh, here's a transaction I committed, but I haven't got the other side of it yet. How do I know, like, who else has updates that are part of this transaction, and like handle it on the consumer side so that I have a transaction when I do my write?
Yeah. So we haven't. This is not yet in the product, but the design that we have for it is the way we do transactions right now is you create a transaction, you go through the transaction manager, right? So you create a transaction, you can write the provisional records for that, and then you commit the transaction. So at every point in time, your transaction manager knows what are the tablets that are involved in that transaction, right? Now in TwoData Center, when we send over the records to the consumer, along with, so we'll be sending over the transaction status records as well, and your status record will kind of tell you what tablets are involved in the transaction and what the status of that transaction is. So on the 2DC side, what we'll end up having is we'll have a waiting for all tablets sort of a status, which means that some tablets will write these records, but they won't be visible yet because you're still waiting for other tablets to receive those records. And then once everybody receives it, we'll kind of flip the switch and say it's committed. So some of this design has been documented on GitHub, so feel free to go and look up the architecture section. So we have like some thoughts on it which are written down. But yeah, the idea is kind of to maintain some status to keep track of whether all the tablets have received the data or not.
Okay, so there is a record of a transaction happened involving these tablets.
Correct.
And here's part of the
Yes.
logs to
Yes.
the individual.
Yes.
Any more questions? Going once?
All right, yeah.